Let us now take a look at prime ideals in integral extensions. So what we want to do is, given any ring extension R into R prime, most often an integral extension, we want to see how prime ideals in R are related to those of R prime. Why would we want to do such a thing? One motivation comes from geometry. So remember that if x and x prime are some affine varieties, then in the correspondence between ideals of the coordinate algebras and subvarieties, prime ideals correspond to irreducible subvarieties. So we want to study the relationships between irreducible subvarieties of x and x prime when we have a morphism from x prime to x, corresponding to a morphism in the other direction from O of x to O of x prime. So the picture is the following that you should have in mind, that we have some ring R included in R prime, and we think of this as usual as O of x prime, and this is O of x. And make it a habit to always draw these pictures and think pictorially and geometrically about the statements and proofs we are going to do. So the simplest example is perhaps the one we've seen before with the diagonal cross over the affine line. So, for example, a point would correspond to a prime ideal P. And here one of these diagonal lines, or any point, would also be corresponding to a prime ideal. So this is the picture to have in mind. And it might also be helpful to draw the corresponding non-integral pictures to see what goes wrong, if anything goes wrong. So to be more precise, if you have any ring extension and an ideal in the smaller ring, then all the R prime multiples of this ideal form an ideal in the bigger ring. Conversely, if you have an ideal in the bigger ring, its intersection with the smaller ring is an ideal in the smaller ring. And if this ideal in the larger ring is a prime ideal, then its intersection with the smaller ring is prime. We've touched upon this at some point. And we want to know the properties of these. So for example, what we will ask is, assume you have an ideal downstairs. Does there always exist an ideal lying over it? Meaning, does there always exist an ideal in R prime whose intersection with R is our prime ideal to begin with? Can there exist multiple? Assume we don't only have one ideal, but an inclusion of ideals. Can we always find a corresponding inclusion of ideals upstairs that sort of goes down or lies over our inclusion of ideals, and so on? These are the questions we want to ask. So let's get started. The first property we want to look at is the so-called lying over property. So again, we always picture the ring R prime as lying over R, or the affine variety x prime as lying over the affine variety x, as one often does in algebraic geometry. And so assume now that we have an integral ring extension from R into R prime, and we are given a prime P in R. Then the good news, there is always a prime ideal P prime in R prime whose intersection with R is P. So we need to show the existence of such an ideal P prime. We will do this in two steps. First, we will wait with P prime and observe the following property, that if we take our prime P, pass it up to R prime, and intersect it with R, we will stay inside P. This is not so trivial to show. So take A in PR prime intersect R. And we want to use some Cayley-Hamilton type argument, but the problem is we don't know if the ring R prime is finite or not. We know it's integral, but to be finite it has to be generated by a finite number of integral elements. We don't know that. However, we can look locally in some sense. So if we have A in PR prime intersect R, well, just in general, so A is going to be some sort of linear combination, P1A1 plus etc. plus PNAN, with the PI in P and the AI in R prime. So we consider M to be the ring generated by these AI. And these will be integral elements, so this will be a finite ring extension. Okay? And now we consider, as usual, our favorite map from M to M that maps an element X to A times X, where A is the element inside PR prime intersect R that we chose. And now we know that because A lies in this thing, F of M will be inside P M because of this property of A. And so we can use the stronger version of the Cayley-Hamilton theorem that will tell us that we will have such a monic polynomial, f to the power m plus, say, cm minus 1 f m minus 1, and so on, c naught equals 0. Now with the ci all in P because of this property and the Cayley-Hamilton theorem telling us that we can choose the non-leading coefficients to be inside the ideal that multiplies to create the image. Yeah, but now apply this to A as usual. So this will imply that we have am plus cm minus 1 a to the power m minus 1. And so on. But everything that includes C is in P because all the Ci are in P. And 0 is of course in P, so this means that a to the power m is in P. But if a to the power m is in a prime ideal, then a has to be in the prime ideal itself. So a belongs to P. So we have shown this inclusion. For whatever reason we chose to show this inclusion, now we have. And now comes the good reason. The second step of the proof is to show that in any extension, integral or not, the property that we just proved is equivalent to the existence of a P prime that we want to create. So, in fact, the integrality comes in the fact that this first theorem held, and it came into our ability to use Cayley-Hamilton because of this finiteness of the ring we looked at. But, okay, so we want to show that such a P prime with P prime intersect R exists if and only if one holds. So first inclusion is that, or first direction is that if there exists such P prime with P prime intersect R equals P, then we want to show that this holds, but this is just some sort of gymnastics of inclusions and whatnot. So we look at this intersection. Now, P is the same as P prime intersect R. So this is P prime intersect R times R prime intersect R. So this is included in P prime R prime intersect R. Yeah, exactly. But P prime is already an ideal in R prime, so this is the same as P prime intersect R, and by our assumption, P prime intersect R is P. So we have shown the inclusion of number 1. PR prime intersect R lies inside P. In the other direction, if PR prime intersect R sits inside P, then we look into sort of localization. So we consider the set S when we want to localize with respect to the prime ideal P. The set S of elements not lying in P, this set satisfies the following condition that when we look at PR prime intersect S, it is empty. So what we can show, so this means that in R prime, this PR prime sits inside some maximal ideal in the localization. And so therefore, this maximal ideal in the localization comes from something in R prime. So we can show that there exists some P prime in R prime satisfying the following two properties, that PR prime is inside P prime and that P prime intersect S is empty. And together, these two conditions can be worked together. I will leave the details to you to show that the intersection of P prime with R is just P. So the idea here is to use the fact that in the localization, things are included in maximal ideals and they come from prime ideals in R prime. So we don't construct P prime constructively, but we know that it exists. When we have this property that we have this ideal P and P prime such that P prime intersect R is P, we say that P prime lies over P. And now pause and draw the appropriate pictures and try to get a geometric explanation of what is going on. Let us go to the next property, which is that of non-containment. And that is some sort of uniqueness condition of the ideals lying over a certain prime ideal. Namely, if P is in R and two prime ideals P prime different from Q prime lie over P, then it cannot be the case that one is included in the other. So this is weaker than actual uniqueness, because in the picture we have here is that if you have something like this, then this point corresponding to P will possibly have two different prime ideals lying over it. But if they are different, then one is not contained in the other. So how to prove such a thing? Well, what we will prove is that assume that P prime is included in Q prime, but they are different. And we want to find a contradiction then. So take an element A in Q prime, but not in P prime. Okay? Now, our ring extension R into R prime is integral. So then we have R mod P inside R prime mod P prime. This is integral because of the compatibility with the quotient. Therefore, in R prime mod P prime, we will be able to write the following equation. A bar to the power n plus Cn minus 1 bar A bar to the power n minus 1 plus and so on plus C0 bar equals 0, where all the Ci are in R. So here I am using the quotient notation using bars. So the quotient projection from R prime to R prime mod P prime is denoted X maps to X bar. So we have this polynomial equation, this monomial equation, because this is an integral extension in R prime mod P prime, and we can assume that it has minimal degree. But then our element A belongs to Q prime. So this implies that C naught bar, so everything here, except possibly for C naught bar, automatically belongs to the image the quotient image of Q prime, so does C0, because it's the remaining term in the equation. So this is here. But C0, the representative, is in R. So this quotient map, this quotient image, will lie into Q prime intersect R mod P prime intersect R. But both of these are P. By assumption, both Q prime and P prime lie over P. So this means that C naught bar is equal to 0, because it lies in the preimage of 0. And in other words, we have this polynomial that now has no constant term. So since we're modding out with a prime ideal, we are working in a integral domain, so we can factor one element A, because now we have no constant term, and factoring this element A, we get a polynomial of lower degree, a monic polynomial of lower degree satisfying that A satisfies. So we can lower the degree, because A is not 0 and we are in a ring without 0 divisors. But this is a contradiction because we assumed minimal degree. So therefore it cannot happen that such an A exists. And this means that if P prime is including Q prime, then in fact P prime is equal to Q prime. And this proves the non-containment proposition. Again, think about the geometric interpretation of this. We can derive some consequences of this. So there are two consequences that are useful, but we will not go into the proofs. You can read about them in the literature. If you have an integral ring extension, then if you are given a prime ideal in the larger ring, that prime ideal is maximal if and only if its intersection with R, which we know is a prime ideal, is in fact maximal. Related to this is the fact that if you have two integral domains in such a way that R prime over R is an integral extension ring, then either both are fields or none of them is a field. This means that you cannot take a field and have an integral extension over it that is not a field. And perhaps more seriously, you cannot take an integral domain and pass it to a field with the help of an integral extension. In particular, the field of fractions over a non-field is not an integral extension. Let us finally touch upon two properties that are useful to know. And the first one is the so-called going up property. So again, we're looking at an integral extension. And if we have P and Q in R prime ideals, with P lying inside Q, so the picture is here, we have P lying inside Q in R. And then we have P prime, a prime ideal, lying over P. So I will write this with this kind of arrow. So P prime intersected with R gives you P. Does there exist Q prime such that we can complete this square? So Q prime contains P prime and lies over Q. And the answer is yes, if the extension is integral. And so I will briefly give a sketch of the proof, or rather the idea of the proof. The idea of the proof is to consider, again, R mod P inside R prime mod P prime. And then you consider Q mod P here. So Q contains P, so you consider Q mod P. This is a prime ideal. And then you use the lying over. So there exists some ideal J in R prime mod P prime such that J intersected with R mod P gives you Q. And then from this, by sort of unfolding from the quotient, you get the existence of Q prime in R prime lying over Q and containing P. So somehow what you do, you collapse this P to 0. And then suddenly the property you want to prove is exactly the lying over property that you have proved. Of course, to do all these mechanisms, there are details to be checked that I will skip. But this theorem also holds. Finally, you might want to think, what is the geometric interpretation about this and of this? And I will leave this to you. And instead go on to the opposite idea, the going down idea. So now we have prime ideal P sitting inside a prime ideal Q. But now what we are given is a prime ideal Q prime in R prime lying over Q. And we ask, is there a prime ideal P prime contained in Q lying over P? In the previous proposition, we were looking for Q prime. Now we are looking for P prime. This turns out, in general, not to be true for any integral ring extension. So we have to assume that the smaller ring R is normal and the larger ring R prime is an integral domain. Then this property holds and P prime exists. I will not give the proof, but I want to ask you to try to find an example where you have an integral ring extension, perhaps just pictorially using geometric images, but where R prime is not an integral domain, and see why this fails. So why do we need R prime to be an integral domain? That is the question for you. The reason we need R to be normal is much more subtle, but hopefully you will find a counterexample when R prime is not an integral domain. And this concludes our properties with respect to prime ideals in integral ring extensions.